Hi everyone, my name is Taein. I'm a postdoc researcher at Wei-Jin University of Oxford. So today I will take over this like a HoloAssist challenge session. So just like to recap what HoloAssist is. So we have a data set that like have one performer and instructor all the time. So they basically whatever people see from performer side, streaming to the instructor, and the instructor gives some instruction to instead of like an AI system. So that like every time performer has some mistake, the instructor intervene the situation and they give like a right guidance. So our data set has around 160 hours data with 350 unique instructor performer pairs with 8 modalities. And 2,243 sessions. So let's move. So in this session, we will focus on mistake detection. So for example, in this task, we want to replace an ink cartridge, but when the performer opens some other place, for example, the paper tray, then it's mistake. And it closed, which is the correct one, and then when open the write the ink cartridge, it's correct. So we wanna detect this type of mistake, and in this challenge, we will present two mistake detection. So first one is a second winner, and then second one is first winner, and then we also cover some usage of a HoloAssist data set next sessions. So yeah, we will start from Constantin. I believe he's here.
So hello everyone. My name is Constantin. I'm a PhD student at TUM, Technical University of Munich. And today, on behalf of my co-authors, I will present to you our technical report on the egocentric mistake detection challenge for the HoloAssist dataset, on which we achieved the second place. So first of all, just once more quick overview of the overall problem setting. So as it is defined for the HoloAssist challenge, the mistake detection is performed on individual fine-grained action clips. However, within our approach, we further wanted to restrict this assumption to an online streaming scenario, where we basically always don't leverage any segmental information, but rather try to predict mistakes in a continuous fashion. And secondly, within our approach, we also wanted to detect several different mistake types. So from procedural to execution mistakes, as they also appear within the HoloAssist dataset. And here, procedural mistakes relate to ordering or skipped actions. And execution mistakes relate more to incorrect motor errors or also tool misusage. And furthermore, we also extend within our approach beyond the mistake detection by also considering providing explanations as to why a mistake might be, a certain action might be wrong, in addition to detecting the mistake. So here you can see the overall overview of our approach. So on the left-hand side, you can see that we expect a continuous RGB video stream as an input. And then we process the individual frames with a vision transformer and jointly consider a Q-former in order to extract the spatial relations within a frame, similar to the BLIP2 architecture. And then subsequently we pass these features into another Q-former that essentially extract the temporal dependencies between multiple subsequent frame-wise features. And here the colored squares indicate the learnable queries. And these features on the lower branch essentially are passed to the mistake detection branch, where essentially we just leverage a linear classification layer in order to then output the corresponding mistake logits. And these logits are further passed to the mistake explanation branch, in particular to the GM, which is a gating mechanism which just leverages a sigmoid function in order to determine when to pass or propagate the features further to the projection layer, which essentially projects the features into the LLM embedding space. And these features are then further passed to the LLM alongside with a prompt. And then subsequently, the LLM outputs the corresponding explanation for the detected mistake. So here you can see the overall quantitative results as of now regarding the HoloAssist mistake detection challenge, where the TS former is just the original baseline that has been reported in the original HoloAssist paper, and the other approaches are just directly taken from the CodaBench benchmark website, where you can see that we overall perform second best. And here, in addition, you can see some qualitative results. On the lower half, there are, in green, our confidence scores that are output by our model. And in blue, you can see the corresponding ground truth annotation regarding the mistakes, where 0 indicates a correct action and 1 indicates a mistake. And then above that, you can also see the ground truth annotations that we utilized from the HoloAssist dataset, because these annotations and explanations as to why an action is wrong are also provided by the HoloAssist dataset, which we use for the explanation generation training. And above that, there is also some exemplary predictions of our explanations. Yeah, this was a short overview of our approach, and thanks a lot for your attention, and thanks a lot once more also for the organizers of the workshop. Thank you.
I'm pleased to present the solution developed by me and the MRCS team for the mistake detection challenge of HoloAssist. The goal of mistake detection is to identify whether a user makes an error while performing a task. First, we analyzed the HoloAssistant dataset and found it presents a two-level long-tail problem. At the first level, mistake events are rare and often ambiguous. This leads to a highly imbalanced dataset, which makes traditional supervised learning quite difficult. At the second level, even with the mistake events, there is a high intra-class variability. That's because the dataset covers many task types and diverse user behaviors from egocentric video. For example, mistakes in belt-related tasks are rare, but for big printer tasks, mistakes are more common. So, this complex setting makes it tough for a single model to perform well, and simply using a balanced loss isn't enough to handle the imbalance. To address these challenges, we propose a two-stage MOE framework designed to exploit complementary modeling strategies at both the feature extraction and the classification levels. Let's start with the first part, called feature MOE. The model takes two types of input: coarse-grained action and fine-grained action. Fine-grained action is a short video clip extracted from a coarse-grained action. For example, if the coarse-grained action is installing a switch controller, then the fine-grained action could be inserting the left controller into the rail. We use VRVIT as a backbone for video feature extraction. VRVIT is pre-trained on the kinetics dataset, so it's really good at capturing coarse-grained human actions. However, mistake detection needs fine-grained understanding, which kinetics don't cover well. So we use LoRa to fine-tune the model for this specific task. We introduce a feature MOE module. It diffuses the output from the two backbones using a learnable weighting mechanism. Once we get the joint feature, we send it into a classification module to decide whether the action contains a mistake. But here is a challenge. The HoloAssist dataset is very diverse. It includes different types of videos and various levels of class imbalance. So, using just one classifier often doesn't work well across all situations. To solve this, we built 3 different classifiers, F1, F2, and F3. Each one is trained with a different strategy. F1 uses a weighted CE. This helps balance the class directly. F2 is trained with AUC loss, which is a distribution insensitive loss. It's widely used in machine learning, especially when dealing with imbalanced data. F3 combines area loss with SAM to improve generalization and robustness. Finally, to bring all 3 together, we use the classification MOE module. It assigns dynamic weights to the outputs of F1, F2, and F3 and fuses them for the final prediction. Here are our results on the test set. Compared to random and transformer, our method shows a clear improvement in F-score. When compared to SOTA method from 2022, we see a big boost in mistake recall. What's more exciting is this: our method only uses the RGB modality but still achieving performance that matches or even beats models using multimodal inputs. That said, we still believe this is a very challenging task. There is a lot more to explore going forward. That's the end of my presentation. If you have any questions, feel free to reach out to me through the contact info on my homepage. Thank you.
Hello everyone, my name is Wei-Jin Huang. It's a great honor to be here at the Egocentric Vision Workshop. Today, I'll present our work on modeling multiple normal action representations for error detection in procedural tasks, a collaborative effort with my colleagues. Our work tackles a crucial challenge in AR, reliable error detection, where existing methods fall short. Our key insight is that procedural tasks often have multiple valid next actions. For example, after grinding coffee, you can either boil water or prepare the filter. Both are correct. This is where prior work fails. Methods using static prototypes or single-path predictions can't handle this flexibility or adapt to real-world variations. Our goal is to build a framework that dynamically models all possible normal actions for robust error detection. To address this challenge, we propose MNAR, which stands for Adaptive Multiple Normal Action Representation. The process begins with an action segmentation module that identifies the sequence of executed actions from the video input. Then comes the core of our framework, the Potential Action Prediction Block, or PAP-B. It uses a task graph and dynamic programming to predict all logically valid next actions. This directly solves the multiple valid actions problem I mentioned earlier. Next, the Representation Reconstruction Block, or RRB, leverages temporal visual features to generate a normal action representation for each of these valid next actions. Finally, the Representation Matching Block, RMB, compares the ongoing action with all the generated normal representations. If the distance exceeds a learned threshold, the action is flagged as an error. This ensures our detection is both adaptive and precise. We evaluated MNAR on 3 datasets, EgoPer, Captain Cook 4D, and especially HoloAssist. Across the board, MNAR sets a new state-of-the-art. On HoloAssist, we achieved significant gains in both EDA and AUC, proving its effectiveness on complex, real-world tasks. This figure also shows MNAR's robustness. When the segmentation model makes a mistake, other methods, like EgoPad, are easily fooled and signal a false error. But MNAR, by considering multiple possibilities, correctly identifies the action as normal, avoiding these false positives. Omna can also detect subtle errors. Here, both actions have the same label. Stir using spoon, but on the right, the action is performed with a knife. Amna looks beyond the label, compares the actual motion, and correctly identifies this as an error. To conclude, our key takeaways are following. First, we uncovered a key failure in existing methods. They can't handle multiple valid next actions. Second, our solution, Amna, dynamically models all valid next actions to overcome this. Moreover, Amna achieves state-of-the-art performance on challenging datasets like HoloAssist, proving it's both effective and robust. Last, we believe our adaptive strategy is a significant step forward for error detection in AR, robotics, and beyond. Our code is available on GitHub. Thank you for your attention, and you can contact me in the following social media QR code.
Hello everyone, I'm Michele Mazzamuto from the University of Catania, and today I'm presenting our work. Our work called Gazing into Misstep, leveraging a gaze for unsupervised mistake detection in egocentric videos of skilled human activities. Detecting the user mistake is fundamental to provide contextualized guidance and in-wearable AI assistance. A standard supervised approach is limited because even defining what a mistake is typically requires domain knowledge. Also, mistakes are open set by nature. New, previously unobserved mistakes can always arise in practice. Gaze trackers are nowadays on many modern devices, hence gaze can be used both at training and at inference time. So can we use gaze to model user behavior and understand when a mistake is made? As we can see in this video from HoloAssist, after closing the paper tray and before making a mistake, the user exhibits some unusual and disoriented gaze pattern. The gaze movement then returns to normal as soon as the mistake ends. So we propose to understand if a mistake is made by analyzing the gaze trajectory. In particular, we start from the assumption that mistake can be identified by abnormal attention patterns, so moments when user may mistake or act like in an unconventional way or deviates from a standard procedure. So we propose a new task called gaze trajectory completion, in which, given a video and a partial gaze trajectory, we regress the final part of it. We propose also gaze frame correlation module that link the gaze information with the video. And finally, to tackle the mistake detection task, we propose to compare the ground truth gaze trajectory with the predicted one in order to assess if a mistake is occurring or not. This can work in an unsupervised manner and also is domain agnostic because we do not need to define what a mistake is. This is our proposed architecture. The model taking inputs a video and gaze trajectory. Then the first half of the gaze trajectory in orange is fused with the video using two proposed fusion strategy. And at the end, after a peak finding operation, the final part of the gaze trajectory is predicted. The core innovation stays in the gaze trajectory completion task and also in the gaze frame correlation module that learns how to link the gaze information with the video, reducing the uncertainty in the gaze prediction because it is conditioned on the initial part of the gaze trajectory. In order to choose the best scoring function and fusion strategy, we performed an ablation study. In particular, entropy performed only slightly better than the random baseline. Euclidean and dynamic time warping improved the result with the best configuration achieved with an heatmap-based approach that consider as a score, as a mistake score, the position of the ground truth gaze inside the predicted heatmap. We tested both the proposed fusion strategy, achieving the best performance obtained using both of them. As standard for mistake detection, we evaluate using F1 score, precision, recall, and area under the curve. As a supervision level, we tested fully supervised, one-class supervised, and unsupervised approach, and we tested on popular dataset, including gaze information and also mistake label, such as HoloAssist, Epic Tent, and industrial. Our proposed approach outperformed the considered baseline, and also this approach was ranked first last year in the mistake detection challenge of HoloAssist. Here we can see a qualitative example. On the left, we have correct execution, correctly classified as correct. Note how the predicted gaze in blue follow the ground truth one in green. On the right, instead, we can see a mistake. Note as soon as the mistake begins with the red label, the predicted gaze in blue deviates from the ground truth one in green. Please, if you have any question, come to our poster session on the main conference on Friday. Thank you for the attention and to organizer for inviting me.
So hello guys, I'm Maia. I'm going to actually be an incoming senior researcher at Microsoft Research, and as Taein introduced, I'll talk a little bit about some work that we did with the HoloAssist dataset, not in mistake detection, but actually in a correlated area, which is confusion detection. So developing assistive technology for physical tasks have been about augmenting human capabilities in these tasks, but these assistants need not to just understand what the environment and the task are, but also user cognitive states, which can affect user task executions. And humans naturally adapt to each other during their collaboration, and we really want AI assistants to do the same thing. So they must be able to recognize and respond to these internal states to provide help that's timely and useful. And so an important cognitive state which affects user performance during execution is confusion. And we see this a lot in the HoloAssist data set. And unmanaged confusion can cause user frustration towards a task and disengagement. So it's important for AI assistants to be able to detect that confusion. And for this work, we're actually going to use a narrower definition of confusion, which is the perceptible moment in time where assistance would be helpful and relevant. So the HoloAssist dataset has many instances of confusion, and it actually allows us to establish a ground truth for these instances. And this is due to the fact that the instructor, who's that person providing step-by-step instructions, also provides follow-up information if they detect the user is confused or if the user asks a question, which is another indicator of confusion. So here's an example where the instructor asked the user to change a GoPro battery. And then the instructor detects that the user is confused based on those implicit behavioral signals and provides additional follow-up information. And ultimately, we want an assistant to be able to do that. So in order for an assistant to have that capability, it needs to be able to detect confusion. And so we need to model this data. And the first thing we did was curate a data set for confused and non-confused specific labels. So we broke down the HoloAssist data set into instruction by instruction execution intervals, where we defined a confused execution interval as one being bookended by the instruction and also the follow-up from the instructor or a user question. We also defined a not confused interval as being bookended by the instruction and then whatever the next instruction is. Additionally, any model we develop needs to be able to accurately detect confusion, both in terms of the task that it was trained on and also be generalizable to previously unseen tasks. So we kept that in mind when modeling. And anyways, this curated data set resulted in 3,767 confused and non-confused intervals. So when coming to modeling on this data set, one of the potential input sources that we could use for confusion detection, which is provided by the HoloAssist data set, is behavioral signals conveyed by the participants. So in the case of the HoloAssist data set, that is hand movement, head movement, and gaze movement. And these behavioral signals reflect user internal models of the interaction that they're involved in, so about the task and about their environment. And we do find that people react behaviorally to confusion. So we took these behavioral signals and pre-processed them into a total of 144 features. And when we looked at those features that we generated, for this data set, we found that there was a statistically significant difference in the behavior exhibited with respect to competent versus confused execution. And so that shows promise in using those signals for classification. So we modeled these signals using lightweight classification models, such as an explainable boosting machine. And the reason for that is that we can then eventually in the future integrate these models for real-time detection into AI assistance. And I'm just going to go over a few of the results to give you some idea about the data set. So the dashed line is random, and the bar you see here is how well a human detected confusion, so a human baseline. And first thing we notice is that when we actually model just the instructions, the instruction embeddings, we do better than random. And this suggests that instructions carry a strong bias. Some are just inherently more confusing than others. Then we also modeled the behavioral signals that I mentioned, and we showed that these signals can be used for detection in these physical tasks, but really we're interested in improving that detection performance. And one way could be through contextualization. So we contextualize these behavioral signals using the instruction embedding and also the time that the user has spent on the instruction. And what we see is by contextualizing the behavioral signals that we were able to improve performance, and it was statistically significant. Finally, we wanted to see how those lighter weight behavioral models performed in comparison with current state-of-the-art deep learning models. So we took the egocentric videos from the HoloAssist dataset and fed them into a deep learning model, which was VJEPA, which was state-of-the-art at the time, and showed that actually its performance, that deep learning model, was not statistically significantly different from our best performing lightweight model. Additionally, we also wanted to see the potential of our technique to generalize across tasks. And so this messy graph, really what we wanted to show is that we, first of all, can in fact to generalize to other tasks that it hasn't seen before. And that, but the performance varies greatly. And this is partially due to the fact that there's great variability in these tasks. And even in instances where there isn't confusion, these tasks require different behavioral signals to be exhibited for successful execution. So the key takeaways from this work is that, first of all, detecting confusion is a complicated problem, and that models trained on behavioral signals have the potential to generalize to tasks unseen. We also saw that these lightweight models trained on the behavioral signals performed comparably to more computationally expensive ones. And finally, that by contextualizing behavioral signals, that holds promise in improving estimation of human cognitive states.
Thanks, Taein. Hi, everyone. My name is Andrist. So I'm a researcher at Microsoft Research as well in the Interactive Multimodal AI Systems group. And in this short talk, I kind of wanted to end the session with something a bit different and tell you about some work that our group has been doing recently around situated collaboration between humans and AI systems in the physical world, and our particular approach to building benchmarks in that space. So first of all, data sets and challenges like HoloAssist and Ego4D and all the rest are fabulous resources, not just for building models and making progress in AI, but also for studying and appreciating the rich complexity of human-human collaboration in physical tasks, around mistakes, around confusion, around everything that you just heard about. But my main message for you today is for more people to consider maybe an additional complementary approach from static data sets towards perhaps building more living benchmarks and challenges around interactive systems that can be continuously situated in specific contexts with real users in space and time. And if you think, for example, just about visual question answering for a moment, the kinds of questions that real people ask when they have a real need in the moment are very different from the kinds of questions we see in benchmarks generated by researchers thinking hypothetically or generated by LLMs pretending to be users. And I'll show some examples of that in a second. But what's exciting about this approach is that we can then go beyond improving an accuracy metric on a data set to solving a problem with real users by integrating our models back into the same interactive system and seeing how things improve. So, that's the main idea and the philosophy. The interactive system that we've been building most recently in our group is what we call Sigma. It's an open source system in the domain of physical task assistance. And the idea is that an AI agent using various LLMs and VLMs can guide people step by step through a procedural task by leveraging the egocentric sensors like the camera view, eye tracking, hand tracking, and so on. For now, it targets the HoloLens 2 device, and we're actively working on porting to other more lightweight glasses. We're working with Aria glasses. And we're currently using this system in our lab to collect new data and build new benchmarks centered on situated collaboration. So let me just walk quickly through a few frames from some pilot data that we've collected with a real participant, just to kind of give you an example of the kinds of challenges I'm talking about. So in this session, the user is following instructions from Sigma to make a button with this unfamiliar machine. So Sigma starts at the first step. First attach the white top cutting insert, blah, blah, blah. The user kind of mutters to themselves the white top cutting insert while looking around. Eventually they grab this piece in their hand and they ask, is this it? The system says yes, more or less. Then there's a long pause while the user continues to look at it, clearly unsure, possibly confused. Then they ask, can you describe the white top cutting insert better? And the system responds with a more elaborate description, and eventually they move on to the next step. Now, thinking about question answering again, a few sub-challenges immediately emerge just by observing this one small interaction. So first, a smart system needs to reason about whether or not a user's utterance is actually a question or not. In this case, for example, they were talking to themselves, and so the system does not always need to respond. And then there's the problem of asking very difficult, highly contextual questions like, is this it? Is this it is a question that makes no sense in text alone. You need to reason about context, about visual modalities, about actions, about everything that's happened so far, just to ground the references involved. And then there's a challenge of answering questions before they're even asked. So in this case, the person was staring at the piece for quite a long time before asking their question. And a smart system could have figured out that an elaboration was needed without waiting for an explicit question. And if you look at the VQA benchmarks that are out there today, these are the kinds of questions I see in most data sets. Stuff like, what is the white object on the wall above the TV? Or what is the color of the towel under the microwave? Again, these are great for probing specific model abilities, specific visual capabilities maybe, but they're very artificial and they're far away from the questions that people ask in real interactions. So I'll wrap up there just with a couple take-home messages. First, there are many open challenges in situated collaboration which require new benchmarks and new approaches. And to address these challenges, I think we need not only more data sets of collaboration, but also end-to-end systems that can interact with users and define new living benchmarks. And so Sigma is one stab at such a system that our team has developed, and it's on GitHub at the link there, so please check it out if you're interested, and please reach out if you're interested in collaborating with us. Thank you.